Hello for everyone. My name Mustafa Muhammad Atiyah. I'm MS student in Al-Mustansiriya University, Iraq, Baghdad. Supervised by Assistant Prophet Dr. Qasim Al-Ambari and Assistant Prophet Dr. Ali Ja'far Mahdi. My paper title Optimum Dynamic Performance of Wind Power System Using Multi-Objective Gray Wolf Optimizer. Content: Introduction, Research, Objective, Modeling of the proposed system, Controlling system, Optimization procedure, and Results. Introduction: Connecting and operating wind energy conversion system requires an effective and good control, and most of the control system use PI controller, but the parameters of the PI controller suffer from poor performance and high sensitivity of nonlinear system like wind power system, and the process of controlling it is very complex and difficult. Therefore, intelligent algorithms are used to perform automatic setting of the parameters of PI controller. In this research, Gray Wolf optimizer were used that simulated the leadership hierarchy of the Gray Wolf community to obtain optimal value of the parameters of PI controller. Gray Wolf optimizer is used in several applications like PV system, load frequency control, and economic dispatch and power system, and wind energy conversion system. Research objective. In this research, Gray Wolf optimizer algorithm is implemented for a grid-connected wind power system in order to achieve the following points. It provides an optimized regulator for obtaining the optimal value of PI parameters. It's capable of handling the difficult restriction and obtaining the best value of the PI controller's parameters. It provides a real-time operation of the proposed system with optimized regulator. Modeling of the proposed system. The proposed wind energy conversion system that used in this research consists of wind turbine directly connected with permanent magnet synchronous generator, three-phase uncontrolled rectifier, DC to DC boost converter, control on the generator side which is called MPPT control, three-phase voltage source inverter, and connected to main grid by LC filter to reduce ripple in voltage and current, and three-phase isolating transformer for the purpose of protection and isolation, as well as control system on the grid side. The variable loads is connected at the point of common coupling. Wind turbine model. The wind power is converted into mechanical power by a wind turbine. Mathematical equation of wind turbine can be expressed according to equation from 1 to 5. When the wind turbine is operated at optimal value of lambda and Cp, lambda optimum and Cp optimum, this means achieving a maximum power irrespective of wind speed variation. Permanent magnet synchronous generator model. There are several types of generator used in wind power application. In this research, we use permanent magnet synchronous generator due to it has several advantages, which is: first, it connected directly with a wind turbine without using a gearbox. Second, it does not need to external DC supply to provide excitation field because it has a permanent magnet material on the rotor. 3. High power density and high power factor. 4. Small size and suitable for low speed application. The dynamic equations of permanent magnet synchronous generator can be derived according to DQ reference frame, and its mathematical equation can be expressed based on equation from 6 to 9. Controlling system. A. MPPT control. The control on the generator side is called maximum power point tracking control, which is reasonable about obtaining of maximum power from wind generator regardless of wind speed variation. Figure 2 represents a block diagram of MPPT controller. The proposed control method on the generator side is optimal torque based on feedback voltage and current control, where the reference value of DC current is provided from a set point of electromagnetic field of the wind generator. This value is compared with actual value of the output DC current of the uncontrolled rectifier, and the error is sent to PI controller to generate a voltage signal, which is compared with a carrier signal has frequency 15 kHz to produce a firing angle to the IGBT switch of boost converter. Therefore, the duty cycle of DC to DC converter is controlled and the maximum power is achieved irrespective of wind speed variation. B. Control on the grid side. The objective of control on the grid side is to maintain DC link voltage at constant value and control on the active and reactive power injected to a grid. Figure 3 clarifies the control scheme on the grid side. The voltage and current of a grid is transferred from synchronous reference ABC frame to rotating DQ frame. This transformation is done by using a phase loop by using a phase angle of grid voltages, which is detected by phase loop method. The DC bus voltage is controlled in a closed loop by using reference DC bus voltage equal to 700 voltage and measured DC bus voltage, which is considered as feedback voltage. The error generating due to the subtracting between two voltages, reference and actual, will be minimized by using PI controller to generate reference DC current. In order to achieve unity power factor, IQ is set to 0. The value of ID reference and IQ reference is subtracted from ID actual and IQ actual, which is produced from transformation ABC grid current to DQ, and the error is sent to PI controller. The output of current controller VD- and VQ- is converted to VA reference, VB reference, and VC reference, which is compared with a carrier signal has frequency 4 kHz to generate firing angle of MOSFET for the three-phase voltage source inverter. Therefore, the synchronization process will achieve between wind energy conversion system and electrical grid. Optimization procedure. The proposed wind energy conversion system that used in this work is a dynamic and nonlinear system. Therefore, finding its mathematical model and transfer function is complex and very difficult. Therefore, a Gray-Wolf optimizer is utilized to obtain the optimal value for parameter of KB and KI. One PI controller on the generator side and three PI controller on the grid side. The objective of the optimization process is to produce the overshooting and minimizing the steady state error, and therefore the performance of the whole system will improve. Integral time square error is used as a fitness function. The equation of fitness function can be represented by equation 10. Optimization procedure. This figure represents a block diagram of a Gray-Wolf algorithm working in the proposed wind energy conversion system that integrated with a main grid. The error of MPPT regulator, the error of DC bus regulator, and the error of current controller is sent to a fitness function. Fitness function gives data to Gray-Wolf algorithm, and the Gray-Wolf algorithm will inject parameter of KB and KI to the system. This process will continue until the Gray-Wolf algorithm achieves optimal value of PI parameters. This process will improve the dynamic performance of the whole system. Results. A. Optimization results. Figure 5 represents a plot of minimum fitness function where a number of iterations is 30. And this fitness function reached to stability cases after approximately 8 iterations, and minimum integral time square error that achieve optimal value of KB and KI for PI controller is equal to 0.1278. B. Simulation results. The proposed wind energy conversion system tied with electrical grid is simulated by using MATLAB Simulink software. The total time of simulation is 12 seconds. Figure 6 represents the profile of wind speed. Wind speed is changed as a step size as seen in figure 6. From 0 to 3 second wind speed is 12 meters per second. From 3 to 6 second wind speed is 7 meters per second. From 6 to 10 second wind speed is 12 meters per second. From 10 to 12 second wind speed is 9 meters per second. Also, the load is variable at simulation time. From 0 to 10 second load is 5 kilowatt, and from 10 to 12 second load is increased to become 7 kilowatt. Figure 7 represents the power coefficient of wind turbine. This value is maintained at optimal value, which is equal to 0.48. This will ensure the effectiveness of the proposed MPPT controller, but the system under Gray Wolf optimizer is better performance because it has faster response and lower downshooting in the instance of variable wind speed. Downshooting of this curve represents a notching that takes place because inertia of wind turbine and generator. Figure 8 shows the response of the permanent magnet synchronous generator speed. From this curve, we can observe the system is enhanced under a Gray Wolf optimizer because it has zero overshooting and a quicker response. Figure 9 shows the dynamic response of DC link voltage under variable operating condition, variable wind speed and variable load. In spite of variable wind speed and variable load, DC link voltage is stabilized at nominal value, which is equal to 700 volts. We can observe that the system under a Gray Wolf optimizer has lower overshooting and it reaches to nominal value faster than traditional PI controller. Figure 10 A and B represents the power system management between wind power, load power, and grid power. From these figures, we can observe the system under a Gray Wolf optimizer has zero downshooting and lower fluctuation than that obtained from traditional PI controller. Figure 11 depicts the grid frequency despite of variable wind speed and variable load, but the frequency is maintained at 50 Hz. But the system under a Gray Wolf optimizer is faster response than a traditional PI controller. Figure 12 A and B illustrates the grid voltage under a Gray Wolf optimizer and conventional PI controller. Grid voltage is always constant regardless of variable wind speed and variable load, but the waveforms of grid voltages under a Gray Wolf optimizer is better due to it has zero over and downshooting and more smoothing and more sinusoidal than that obtained from traditional PI controller. Thank you for your attention.